So we got this idea of motion maps, and we talked about how ticker timers operate, and we've got these ticker tapes down below. We got to go through the questions. Obviously, we could go through and talk about what the motion is for each of these. I'm just going to say out loud for this one, okay? It looks like A is moving along, could we say at a constant velocity? Okay. Looks like B is going at a constant velocity, but would you agree faster or slower than A?
Slower.
I would say slower. All right. C, is it a constant velocity?
No.
No, not a constant velocity. In fact, if we're reading from left to right, speeding up or slowing down? Looks like it's speeding up. Yeah, I heard the word positive acceleration. D, definitely not a constant velocity. Speeding up or slowing down?
Negative acceleration.
Slowing down, maybe negative acceleration could be a word that's used. E, is this constant velocity?
Yeah.
Yeah, in fact, I would say, look, if I compare C and D, their total displacements are the same, and the amount of time that goes by is the same. So while this one's constant velocity and this one's speeding up, accelerating, increasing velocity, what would you say about their average velocities? Yeah, should be the same. Total displacement the same, total time the same. Same average velocity, okay? Remember, we have a strict definition for average velocity. It's total displacement divided by total time. And then when I get down to this one down here, this one, changing velocity or constant velocity? Constant. Now, before I go any further, I think I want to go back to 2A. At 0.5 seconds, which one has gone the farthest? Now, the initial statement said that each dot is 0.1 seconds apart. We talked in context why we would use 0.1 seconds apart, because the ticker timers that we use have a 60 hertz frequency. So typically, we would use every sixth dot, and 6 dots at a 60 hertz frequency would mean that every sixth dot would occur at 0.1 seconds. So there's like a reason for why we're using 0.1 seconds. It's not just because I want to tell a 0.1 second story here. Now, keep in mind, when we do this as an experiment, I'm going to say that the frequency is 60 hertz, but I'll say it's 60.0 hertz, which means that every sixth dot isn't just 0.1 seconds. We'll say that it's 0.100 seconds, 3 sig figs, 3 sig figs. That 0 before the decimal doesn't count as significant figures. So we'll have 0.100 seconds for the amount of time between every sixth dot. Okay, so that's more information than we asked for, but I just wanted to bring it up now because it'll come up later. All right, so question A says, after 0.5 seconds, so 0.1, 0.2, 0.3, 0.4, 0.5, and you guys can do your counting, all of these occurred over the course of 0.5 seconds. So I'm just going to write 0.5 seconds on each of them because they all took a total time of 0.5 seconds. So after 0.5 seconds, which one has gone the farthest? Somebody shout it out. Which letter? Watch your language. What is it? F? All right. So we're going to say F went the farthest. I'll make a little note of that. F. Which objects travel with constant velocity? First, let's just answer that. Which ones are they? Then we'll talk about how we know. A. What's another one? B. E. F. All right. So A, B, E, F, and then somebody who I haven't heard from. Can somebody tell me, how can I tell, qualitatively, how can I tell that they're moving at a constant velocity? Yeah? I love that. The dots are evenly spaced. That's a nice qualitative way to talk about it, right? In other words, we're covering the same amount of extra distance each time interval. And if I was thinking about that as like a data table, that would mean that the first differences were all the same. If I was thinking about it as a graph, it would mean the graph of a position time graph is a constant slope. Those would be different ways to interpret this. But in terms of looking at just the strip, I would say evenly spaced. That would be a nice way to talk about it. So C, which objects travel with constant oh, I forgot to say, rank them in order of increasing speed. Okay, so before we go on, which one's the slowest?
B.
B is slow? Okay, so I'm going to say slowest. And then we'll bracket that. Which one's the fastest?
F.
Fastest. So whatever order I put this in, B is going to be first, F is going to be last. Which one is the next fastest after B? Or sorry, next slowest, I should say. A. And then I made this sort of rambling conversation about these two having the same average velocity. Could we even agree that this one in the middle has the same average velocity?
Yeah.
So in terms of fastest or slowest, couldn't we kind of just say that all three of those are the same speed? So I want to say that, yeah, they could all be the same speed. I'll put them in brackets, though, because we've got C, D, and E are all the same average velocity, and they're in between A and F in terms of average velocities. But then if I was going to rank things in terms of increasing accelerations, I could say, hey, let's have a thought break. I've got C, D, and E. Which one has the highest acceleration? Or sorry, the lowest acceleration, because we're going to rank it from lowest to highest. Which one has the lowest acceleration? Looks like E is 0, right?
But D has a negative one, so then technically negatives are less than positives.
Yeah, negative acceleration is lower than positive, so I could say D and then E, I guess. So a negative acceleration, then a positive acceleration. Is anything else accelerating? Doesn't seem so.
D is accelerating.
Or did I say D? Not D and E. Sorry. D is the negative one. C is the positive one. My bad. Yeah. All right. D. When do any of the objects have the same average velocity? Now I've said it already. Which are the ones that have the same average velocity?
C, D, E.
C, D, E. I bracketed them up above. C, D, and E. And then calculate the average velocity for each interval and check your answer to D. Use a ruler to measure the displacements. Now, I don't feel like I really need to do all of these. Could we just agree that all three of these line up with each other and all three of these line up with each other? I came along with a ruler and I measured this while you folks were working, and I found that from the origin to this point here was 11.5 centimeters. Fair enough? And if I measure that to be 11.5 centimeters and they all took 0.5 seconds to occur, yeah, I could calculate the velocity. I could say, okay, well, the average velocity for all three of those was equal to delta D total divided by delta T. And I could say that that's equal to 11.5. I could say 11.5 centimeters. That would give me a non-SI unit of centimeters per second. But just for argument's sake, 11.5 centimeters divided by 0.5 seconds. Somebody help the fella out. What's 11.5 divided by 0.5?
23.
23. You should be able to do this one in our heads, right? 23 centimeters per second. And then I could look at these other ones. You know, again, while you folks were working, I made a note. This one here was 7.5 centimeters. This one here was 4.0 centimeters. And this one at the bottom was 15 centimeters. And we could go through the process for each of these. But it's going to be delta D total divided by delta T for each one of them. And so essentially what we're going to end up doing if we rank these guys from fastest to slowest or from slowest to fastest is we'll look at the one that traveled the least amount of distance in the same amount of time compared to the next amount of distance, compared to the next amount of distance, compared to the next amount of distance, and that would rank them in order from slowest to fastest. And so I'm not going to occupy a lot of time with that one. I'm going to expect that we could be able to do that, okay? And so we have that control variable that we've looked at them all for the same amount of time, and that's going to allow us to make that kind of a conclusion, okay? I'll stop there.